Greetings, everybody. My name is Abel Clay Gmail. I'm the project manager for this company, ANTERAS, and we are from Group 16. So let me brief through the introduction of our project. So our company, ANTERAS, is tasked to improve the palm oil harvesting process. So a new electric palm cutter solution is proposed, and we must design the product to be practical and cost effective and sustainable. Mechanical modeling and simulation was used to improve the design. Sociological, environmental, and sustainable factors must be considered, and lastly, theoretical solution used to analyze the design. This is the problem statement for our project. So firstly, palm oil harvesting rely on heavily labor job. The past COVID-19 epidemic causes a shortage of authorized foreign labor. So our company must propose an electric palm cutter tool that will replace manual harvesting equipment. So our goal is to design a viable, cost-effective method that reduce labor and increase productivity. So our tool must emphasize on user-friendly and must be safe to use. Our objective is to design an efficient and eco-friendly electric palm cutter. Second is to validate and optimize electric palm cutter design through simulation, modeling, and theoretical analysis. And lastly, to determine the economic sustainability of manufacturing the electric palm cutter. So our project flow start with a design solution. So we identify on what type of design to be considered. Next will be to identify on what type of material to use. Next, on the material selected, we must perform mechanical analysis. From there, we perform modeling and simulation on every parts and component of the electric palm cutter tool, and we identify on what type of electronic components for our electric palm cutter tool. After that, we perform thermodynamics and fluid analysis. From there, professional and ethics is done. Next will be to identify our economics and finance. And lastly, identify the manufacturing process for our electric palm cutter tool. And that's all for me. So I will pass the next slide to Iman Hakim to present. Thank you very much.
This is the overall design of our electric palm cutter. Our palm cutter has 3 poles, in which the first and second pole is made of magnesium SH31B alloy, and the third pole is made of aluminum 6061 T6. The palm cutter is 3 meters in length, and the total weight of the palm cutter is 5 kilograms. The right figure shows the exploded views of our palm cutter and the component involved. This is the close-up views of our palm cutter, in which the main component are the saw blade, motor, and belting system. All the material used for the head unit of the palm cutter has been analyzed thoroughly. A static analysis has been performed using SolidWorks in order to determine the strength, stability, and deformation characteristic of the palm cutter under static load. The simulation included the addition of fixed support at the handle of the pole, and the gravity was placed at the centroid of the palm cutter, and a load with magnitude of 250 Newton, which is the combination of maximum cutting force and pushing force, was placed at the tip of the saw blade. The result of the simulation found that the maximum stress experienced by the second pole, counting from top to bottom, is about 36 megapascal, and the stress at the third pole is 14 megapascal. The end of the pole was also found to deflect as much as 2 cm. It is important to note that the deflection limits vary depending on the code used for the design of structure. But in the case of a pole for cutting tools, there are no specific deflection limits. However, based on the application, it was safe to conclude that the 2 cm deflection of the pole is within an acceptable range and does not significantly affect the cutting performance. The natural frequency is the frequency at which an object or system naturally oscillates when it is not subjected to any external forces. The result of the simulation found that the natural frequency of the palm cutter is around 1.3 Hz, 21 Hz, and 25 Hz. It is important to know the natural frequency of the palm cutter in order to avoid resonance frequency. By designing the palm cutter to have a natural frequency, that is different from the frequency of any external vibration that the pump cutter may be subjected to. Fortunately, the pump cutter will be operating around 8 Hz to 17 Hz, in which the range of the frequency would not cause the resonance to occur. Vibration analysis is also carried out to analyze the stress experienced by the pump cutter during operation. As mentioned before, the pump cutter was subjected to vibration around 8 Hz until 17 Hz. In the simulation, the vibration source is placed at the saw blade as it is rotating during operation. The stress experienced by the pole is said to be the highest when the source of the vibration operates at 17 Hz. The second pole and third pole experience an additional stress of 16 MPa and 34 MPa respectively, while the third pole will deflect as much as 2.8 mm. Based on the table, the maximum total stress experienced by the pump cutter under load and vibrating condition is happening at the second pole, which is 52 MPa. For the simulation, it is safe to conclude that the pump cutter does not fail since it does not exceed the maximum allowable stress, which is 100 MPa.
So our mechatronic component consists of firstly, a 3S LiPo battery, Arduino Uno 775 DC motor, 2.5mm copper grade wires, potential meter, 80 rating brush ESC, electronic speed controller, jumper cables, and lastly, temperature sensor. So our sensor for this electric pump cutter is a temperature sensor. So the purpose of the temperature sensor in this electric pump cutter tool is to monitor the temperature of the motor. This can help to prevent overheating and potential damage to the motor. So the temperature sensor is typically a thermistor will be placed near the motor and it will detect the temperature of the motor. The sensor will send this information to the ESC, which will use to determine the current temperature of the motor. If the temperature exceeds a certain threshold, the ESC will take action to protect the motor from overheating. So this is the schematic diagram for our electric pump cutter tool. So as shown in the schematic diagram, the signal wire from the ESC is linked to the Arduino Uno board, and the 3S lithium polymer battery is directly attached to the ESC to provide power. The potential meter is then attached directly to the Arduino board pin. Regarding the Arduino board power supply, the ESC is fitted with a battery limiter circuit, which stands for VEC, which is an circuit electronic voltage regulator used to provide power to a subsystem at a variable voltage without the need for an additional battery. The ESC-BEC connection is rated at 6 volt, which is sufficient enough to power the Arduino board. Finally, the output power port of the ESC motor is linked to the DC motor. So I will explain on how our coding works. So to control the speed of the ESC using a potentiometer, the Arduino will read the analog value from the potentiometer and convert it into a PWM signal, which stands for pulse width modulation, because the AC only can read PWM signal. The signal is then sent to the ESC, and the PWM signal will control the speed of the motor by adjusting the duty cycle. So this is the flowchart for our project. So I will explain on how the working principle of our electric pump cutter tool. Due to safety mechanism in a cutting tool, the throttle must be at 0 position when the system is turned on. Otherwise, the cutting tool will not work. If the throttle is set to 0, the ESC will begin functioning. After adjusting the throttle to a suitable speed, a signal is sent to the electronic speed controller, which regulates the amount of power supplied to the motor. And this allows the user to perform in cutting operation. And lastly, the system includes an overheat protection features. So when the motor is running at above 90 degrees Celsius, the system will then turn off for safety reason. So these are the list of safety features that we include in our electric pump cutter tool. Firstly is the low voltage cutoff. So if the lithium polymer is operating at below 7 volt, the system will shut off. Second is zero throttle safety. So initially, before we start cutting operation, make sure the throttle is set to zero position, or else the system will not work. Third will be the overheat cutoff. So if the motor is operating above 90 degrees Celsius, the ESC will automatically turn off for safety reason. Lastly will be braking system. This is to prevent the saw blade from spinning freely after the system is turned off. Thank you very much, and that's all for me. So I will briefly explain on our working model for this project. So this is the method of fabrication. So fabrication involve welding, epoxy, adhesive bonding, grinding, mechanical fastener, soldering, and lastly coating. So this is the picture of our finished product for our project.
The table shows the general specifications of the chosen motor. The NEMA standard provides 4 classes of motor insulation, which describe the insulation system ability to withstand a certain temperature while giving a specific operating life, to address the risk of failure of the insulation due to heat. As we can see from the table, the insulation class of the motor is Class B. Class B motor means the maximum winding temperature is 130 degrees Celsius, with a permissible temperature rise of 80 K under continuous operation. A thermal simulation was conducted under this condition, in which the convection heat transfer coefficient for air was set to be 25 watt per square meter Celsius, and the heat transfer coefficient for the body of the DC motor was set to be 15 watt per meter Celsius. The heat generated by the DC motor was assumed to be located at the center of the motor, and the heat generation rate was based on the power consumption of the motor and the expected efficiency. Based on the result of the simulation, the maximum surface temperature of the DC motor could reach up to 107.5 degrees Celsius under continuous operation of at least 1 hour. It has the risk to exceed permissible winding temperature, and cooling system is much needed. In order to reduce the surface temperature of the motor, a heatsink has been added at the top of the motor. An analysis has been carried out to find the optimal spacing of the heatsink. Figure on the right side shows the design and dimension of the heatsink. Based on the new simulation, it is clear that the attachment of a heatsink with the same condition as the previous simulation result in a significant decrease in the temperature of the DC motor. Specifically, the temperature drops from 107.5 degrees Celsius to 94 degrees Celsius. This demonstrates the efficacy of the heatsink in dissipating heat under natural convection conditions. However, the result of the temperature drop is not enough to prolong the lifespan of the motor. Hence, in the next section, we will discuss a way to further reduce the temperature.
For the design considerations, a constant overall surface area of the fins need to be maintained, fluid flow conditions need to be predicted using a dimensionless parameter and experimental findings to calculate the heat transfer coefficient. These are the assumptions, which are steady operating conditions exist, air is an ideal gas, the atmospheric pressure at that location is 1 atm, the thickness of the fins is very small relative to the fin spacing such that equation for optimum fin spacing is relevant, and all fin surfaces are isothermal at base temperature. After doing the analysis, it was found that the heat transfer coefficient of air, which is the requirement, is 22 watt per meter square per Kelvin. The air velocity is 3.5 meter per second, and the minimum power output is 0.06 watt. The rate of forced convection is 77.5 watt. 64.2% of heat generated by the motor is dissipated, and the surface temperature of the motor is 79.82 degrees Celsius under constant use.
Total production cost. The total cost in manufacturing refers to the sum of all costs incurred in the production of goods or services. As we can see, total cost equal to total fixed cost plus total variable cost per unit multiplied by the number of unit production. So in our analysis, the fixed cost consists of the machinery cost and the factory building cost, whereas the variable cost consists of material cost, labor cost, and utility cost. So after calculating the fixed cost and the variable cost per unit, we get the total cost equal to Rm 598,044. Selling price. Based on the three benchmark harvesting tools that match our design specifications, we take the average cost of them, which is equal to 3,141 ringgit. After that, we set the target margin as 30%. Therefore, the selling price for our product is 4,084 ringgit. 30% rate was chosen as it is a good margin in finding the balance between the desired profit and reasonable price for customers, as our harvesting tool is quite superior, where it is powered by electric, weighted about 6.5 kg, and has extended pole that can reach 2.3 meter. Break-even analysis. The break-even analysis is presented in the graph shown above. In this part, I am calculating the break-even point for our production. The break-even point is the level of production or sales of company's revenue is equal to its total cost. At this point, the company is not making a profit or a loss. The break-even point in the chart, as we can see, is equal to 75 units. So, the company needs to sell 75 units per year to cover the total fixed cost per year. We continue in the break-even analysis. From the graph, the company will start to gain profit after reach the break-even point, which is 75 units, and it occurs in the third month of operating by assuming that the productions are all sold out each month. After calculating the difference between the revenue and the total cost, we get the total profit per year is equal to 774,219 ringgit. Return of investment. Return of investment, or we call ROI, is the efficiency of the company to turn the investment into benefits that higher than the initial investment. By using the formula revenue minus initial investment over initial investment, we get the ROI equal to 129.5%. ROI is one of the important elements that investors concern about before deciding to invest. We can conclude that our design harvesting tool is valuable since the investment is successfully generated into high return. Depreciation cost. Depreciation, which is also known as salvage value, can be defined as the reduction in the fixed asset cost until the asset value becomes zero or negligible. Companies can know the value of their assets over time using depreciation concepts, and their profit will not be damaged during the selling or disposal process. For this analysis, the 5-year time range is taken as the depreciation rate. Therefore, we get the depreciation rate is equal to Rm 184 ringgit per year. Benefit cost analysis. Benefit cost analysis, or BCA, is a method used to evaluate the economic efficiency of a project. It is used to determine whether the benefits of a proposed project or policy outweighs its costs. The benefit cost ratio is calculated, and we get the ratio is equal to 2.29. The product's benefits cost ratio is larger than 1. As a result, the production will achieve economic sustainability and net profits, as well as meet the long-term operation. SWOT analysis. SWOT analysis will help a project to satisfy the customer requirement and product specifications by maintaining the strength, implementing the opportunities, removing the weaknesses, and also considering the threats. So these are the SWOT analysis of ANTERAS cutting tools.
For our manufacturing process, we comply to standards and guidelines which involved in our manufacturing which is the ISO ICS 53 and OSHA 1926-602. For the ISO, it provides standards for material handling equipment, including lifting equipment and industrial machine, and OSHA, it provides a description for health and safety regulation during material handling. The configuration of our design component, we have divided into three parts, which is the head unit, the pole, and the battery housing area. For the first one, which is the head unit, it includes bearing, bolt, motor, synchronous belt and pulley, saw blade, the saw guard, heatsink, and cooling fan. Further, we move to the mid section of our design, which is the pole and the grip handle. As we can see, the grip handle was attached through screw and clamp. Furthermore, for the battery and electric module housing, it includes electrical components such as Arduino Uno, copper grade wires, potentiometer, ATA brush ESC, and lithium polymer battery, which is covered by the electric module housing. From all the listed configuration in our design component, we tend to manufacture our own parts, which is the aluminum alloy pole, saw blade safety guard, battery module housing, and the handle grip. As we can see, the pole includes annealing, drawing, cutting and grinding process as the finishing, and the saw blade, it includes cutting, forming, welding, drilling, and grinding. And the module housing, it applies cutting, forming, welding, drilling, and grinding process as the finishing process. And finally, handle grip is done by 3D printing, and lastly finished with surface coating with liquid acetone. We move to the material handling and storage system. We apply three types of system, which is by using the manual pallet jack, static shelving, and packaging crate. At low volume of flow, we will require to get a few materials from one work center to another or station to another station by using manual pallet jack. The static shelving, despite being less flexible due to their permanent location, it is chosen as our temporary storage for supplies and work in progress. For the packaging crate, we tend to store and package the finished part in a specially constructed packaging crate. The crate's design and capacity should allow for the inclusion of all product parts within the absorbent materials. Next, this is the proposed production plan layout. As we can see, our warehouse includes 6 types of stations, which is the raw material storage, manufacturing workshop, assembly and finishing area, the finishing area, QA/QC inspection area, and production storage area. The arrow indicates the flow of process for each cycle of our manufacturing process of the electric pump cutter.
Under the Code of Conduct, under the Registration of Engineers Regulations 1990, engineers need to have professional responsibility, professional competence, professional confidentiality, and professional conduct. These are the laws and regulations that need to be complied with, which are the Factories and Machinery Act 1967 and the Trade Description Act 2011. Under Factories and Machinery Act 1967, we have 2 regulations, which are Section 11, persons exposed to explosive, inflammable, etc. substances, and Section 24, personal protective clothing and appliances. To comply with this law, adequate personal safety equipment needs to be provided, fire extinguishers and other fire protection measures need to be provided and be readily available. Electrical wires and cables must be in excellent shape and must not be frayed or damaged. Ensure the welding area is clean and clutter-free to minimize tripping and other mishaps. And ensure that all welding equipment is correctly maintained and in good operating order. To comply with Section 7, false trade description, ensure the information regarding the palm cutter is correct and thorough. Avoid inaccurate or misleading remarks regarding the palm cutters or inflating their capabilities. Avoid using unclear or misleading words. Provide facts to back up claims regarding the performance and capabilities of the palm cutter. For quality assurance and quality control, visual inspection of the blade needs to be done. The motor needs to be tested for its functionality. Safety testing of switch and wiring needs to be conducted. The durability testing of the handle and housing needs to be conducted. The performance testing of the cutting ability also must be tested before, and compliance testing of electrical and safety requirements. The work activity are tabulated into table, and then it's further categorized by hazard identification, risk assessment, and risk control. Risk assessment deals with the likelihood, severity, and the risk, and the existing risk control, while the control measures deals with how to control the risk posed by the work activity. In conclusion, an efficient and eco-friendly palm cutter was designed. The electric palm cutter was optimized through various simulation and analysis, and the palm cutter is expected to be profitable and economically sustainable.